Well, hello, Osborne. Osborne, how are you? So, our today's session is mostly about um, more exploring or in-depth exploring in AI and machine learning, and we shall try to connect what we did last time. So, logic. We shall start from wherever we stopped last time. So, logic regression and classification to understanding the nuts and bolts of decision trees. So I don't know if Osborne will take us through or I should just continue. Osborne, are you in a position to present? Osborne? So, um, okay, I'll just wait for a second. Um, but yeah, we shall wait. So I shall take you through machine learning. Once again, I'm Beth Jerry Kimani, and I am your track co-lead in AIML in Google Developer Groups. And we shall be going through, let me share my screen. So, yeah. Yeah. So we shall be going through introduction to decision trees, classification and regression, entropy and Gini, and implementation in Python. So um, um, Decision trees are a non-parametric supervised learning method that is used for both classification and regression. So, and it is one of the most intuitive algorithms because it predicts target values by learning simple decision rules, essentially the if-then logic from your data. So to understand how it works, I will share. Uh, I'll share this tab. So to understand it better, we shall use this. We shall use this tree or this diagram, and I shall try to explain in depth on what I mean. So a decision tree has three nodes, and we have the root node, and we have the decision node, and we have the leaf node. So the what the root node represents the entire population or a data set before any filtering occurs. And for the decision nodes, they are the intermediate points where data splits based on specific features or rules. So you can see as a decision node, we have branches, and this is where we get data splitting into various nodes. And then we have the leaf nodes, and this is the final terminal nodes that provide the output or the prediction, and the decision trees do not go further the leaf node. So think of it like a flow chart. So we start with the root node, then we move down to decision nodes where data filters through rules, and then finally we land at leaf node, which is our final answer. So we shall try to understand this this diagram really well. I shall take you process by process. So yeah, I see Osborne is back. So I'll after I explain this, I think we shall collaborate further on the later slides. So Osborne, just to catch up on slide number, I'm on slide I'm on slide number 3. So um so as I said, so the root node is like the very first, and it's at the very top, like you can see here it is. And what the root node basically does is uh, it represents the entire data set of the population. And then as we move down to the decision node, this is where we encounter decision nodes, and these are points where data splits into specific rules or features, and each split is determined by a criteria like entropy or Gini impurity. We shall go deeper into that. And this ensures the resulting groups are more purer. And then the leaf nodes here, they're the final ones. So if we are to use this, if you're to put the idea into conceptualization, so we have the root node asking, is it sunny, right? So uh, say for example you're planning on going outside to play, say, tennis, and you decide to use a decision tree to determine whether you'll go out and play tennis or you'll stay in since the weather isn't as favorable. So the root node is playing tennis. And then we split down into the decision node. Is it sunny? If no, is it raining? So if it is raining, then do not play. We go back to the decision node. Is it sunny? No. Is the humidity high? If yes, do not play. Or is it sunny? Yes. Is the humidity favorable? Yes. Then we can go play. So that is like in a nutshell what the decision node does. So and if you want to like in depth to get like an in-depth concept of this, you can try to solve a lead code question. Lead code number 37. It is more on decision trees, so you can try that. So the key concepts in summary, we have the root node, the decision node, the leaf node, and the branch. So Osborne, are you in a position to present? I can let you share the screen and you start from slide number 3.
Hope you can hear me now.
Yeah, I can.
Okay, nice. Yeah, I can proceed from here then.
Yeah. So I had reached slide 3, so you can share.
I don't know if I have this specific slide that you're sharing.
No, it was just an illustration.
Okay, okay.
Yeah.
So yeah, so as you've said, um, we have the root node, decision nodes, and the leaf nodes, as you've clearly put them. Um, the root node represents the entire population, decision nodes. Now it's where the data is split, and now after that, the decision nodes are split even further to final output or terminal nodes. So I guess I'll try to share my screen or whatever I have on my side. Okay, just a moment. Yeah, so I believe this is how it should look like. So the first one is the root node. Then the second layer are the decision nodes. Then you have the leaf nodes right there. So as you can see for this one, we have um, for the right ones, we have a condition that is true. Then on the left, it's false. From the root node, we have the decision nodes. For assets greater than 6,000, go to false. For job is equal to part-time, that's true. That one's for the decision nodes, which are split even further to the leaf nodes, where the final decisions are made. Um, yeah, so we can now get into entropy, which Beth has mentioned. So entropy is actually something that measures the impurity or randomness of the the condition. So for higher entropy, that means there's high disorder when you, yeah, basically when you're doing the formula using the entropy formula, and you find that the entropy level, the value is high, then it means the there's high randomness and disorder in that particular structure or data set. Yeah, so that's basically entropy. So the reduction in entropy achieved, I don't know if I have that one. Yeah, from the image that shared, entropy, the entropy formula is was shown as from the image. Then for you to reduce the entropy, because if high entropy gives you high disorder, that means for you to reduce the entropy so that there is less disorder and randomness, you have to partition the data, and the goal here is to maximize information gain at each split, so that at least when you're doing the analysis, or uh, when you're making the final decision, then you have it's easier for you to actually the order is high, or the order is, how do I say it? The order is in a in a structure that is expected, and that makes sure that information gained from this uh, the data is actually accurate and as expected. So that's what entropy reduction in entropy does. It's to make sure that you maximize the information gained from that one. Then then there's the Gini impurity, which is something that measures how often a random element is correctly. Just a minute, let me share that screen. I'm seeing my screen. I hope my screen is visible.
Yeah, yeah, you are visible.
Nice. So yeah, so then there is Gini impurity, which measures how often a random element is incorrectly labeled. So lower Gini indicates a purer node. So that means a higher Gini indicates that that specific node is not as clean as expected. And that is the formula. So yeah, um, I want to go back to that specific part where I wrote. I want to go back to that specific example that I had, that specific document that I had. Yeah, so here we are. So let's look at this example of code, writing a function that implements this rule set for this specific sample is where um, we have records, then we have for when condition is true, then it means the job is part-time. And when the condition is false for the records, it means the assets are greater than 6,000. So, so when we write our code, this is what it looks like, looking at uh, defining assess risk for the client. Then um, if the client records is equals to yes, that means the client job is part-time. Else return okay, which means uh, going back to the closing the else, that means for the false, if the condition is false, then the client asset is greater than 6,000. Um, so we can take one record to test. Then we have training the data frame, or the having the using the iloc function, iloc, to get the output as shown. We have uh, yeah, when we take the the record to test the train data frame using the iloc, to we find that the output as shown is um, assets, as you can see, is 10,000. Then the amount is 1,000. Then we have price is equals to 1,400. So when we look at this data set, our first condition was records is equals to yes, because um, if you have the records is equals to yes, from this one, then the job is equals to part time. If false, then assets are greater than 6,000. So I believe for this one, we have job is a freelance, which means that this one is the records are no, as you can see. Then, so that means we go back to left. So assets are greater than 6,000. So we've already moved from the root node to the decision node. And from here, then you can see that the asset is equals to 10K, meaning that it meets this condition for assets greater than 6,000. Then that means for if assets are greater than 6,000, we go to true because it's 10K. That means it's okay rather than going to the false, which is default. So for this particular client, it goes to the final node as true, meaning for this particular client, when we do, when we the output and the final result from assess risk will be okay as displayed here. So for training a decision tree, before we can train a decision tree, we first need to import the necessary packages. We have the decision tree classifier, we have the dict vectorizer, and we have this ROC area under curves core, which are the packages that are needed so that you can train a decision tree to work as expected. So um, yeah, so we have that one. And after importing these necessary packages, now in your workspace, you can now actually work with or write code so that from the packages that you've installed, this necessary, which are necessary for this one, then your code will definitely train the model using the train the decision tree. Um, yeah, so we have the train dictionaries, um, training the data frame into a list of dictionaries, then turn this list of dictionaries into a feature matrix. So after training, we have the fill NA, which fills all null entries, and then we have the orientation is equals to is going to be the records. Then we get the first I believe the first from 0 to 5, the first 5 records. If I'm not wrong, you can correct me, Beth, on this one. But yeah, this
I
is
think you're on the right track.
okay. Okay, so yeah, so this is what we have output. This is the output we expect from our data. Seniority, then homeowner, and all those things. As we can see from this one, um, we have the records as no for the first one. That means and the job is freelance. So if we go back to our table, if the record is no, that means it goes to this decision node for if assets is equals to 6,000, either true or false. So going back here, we have yeah, no, that means the job is not part-time, and now the job is actually freelance. Yeah, and as you can see from the decision node, we had assets is equals to 10K, which means it's for this particular decision node, it's true. That means the final node will output okay. Yeah, so that's the first one. We have this one, which I believe you get the idea. And this one, for this one, if record is equals to yes, then we have job is equals to fixed. If this condition isn't met, because if for the decision node that we had earlier, we had if job is equals to part-time, then we have uh, goes output is default. But if job is not equal to part-time, and as you can see, that one was, what was it again? Yeah, fixed, then the output is okay. So this is the output you expect from our, yeah, our code. Yeah, then we have using the dict vectorizer package, we try to um, yeah, using the dict vectorizer package imported earlier as the first thing we need to do, it kind of organizes our data and does it turns them into dictionaries, arranges them, or yeah, just make sure that our output is prepared in a list. Is it a list of dictionaries? Yeah, then we have it stored in the X train. Then we using the fit transform, we have the the output as displayed as the array displayed over there. Yeah.
So um husband, I encountered, there was a time I was trying to bring decision trees into light, and I got a question from one of my students, and they were asking if it is right to associate instability case with the condition or the parameters during training of a tree. So basically, you can, as you can, we could see we what we did. We first did the data preparation. That is where we like imported the, we use scikit-learn. Mostly scikit-learn is used in machine learning models. It's the biggest. So and so we did some bit of data preparation, and we split the data into training and testing, and we did some training, and then we did some fitting, and then we did some model evaluation, and then we executed. So the accuracy score, and we were able to like calculate the accuracy by comparing the actual levels and what the model would guess. So their question was, is it right to like associate instability case with conditions or parameters that are used during training of a tree? Um, do you have like a concrete answer, or like I could take us through that?
Yeah, come again on the question.
So the question is, we are training, we are training the tree, right? So is it right to like associate instability case with the condition or the parameters used during like training of a decision tree?
I think I got that part on instability case, but then I think I missed you a bit again.
Can you hear me right now?
Yeah, right now you're okay. I can hear you.
So the question is it right to associate instability case with the conditions or parameters that are used during training of a decision tree?
That's a good question. I'm not sure. I guess I'll get back to you on that one, but maybe you could take us through that one.
Okay. Well, when we are trying to like see if it is okay to like associate instability cases with conditions or parameters used in training, yes, it is correct. You can associate instability with specific conditions and parameters used during training of a decision tree. And in machine learning, instability, which is often known as high variance, means that even a small change in the training of the data can result to a completely different tree structure. And this behavior is directly tied to how the tree is configured and grown. So, for example, if we shall go deeper when we're looking at the disadvantages where we'll have overfitting and maybe sometimes underfitting. And in other cases, we have instability, as I'm talking about it right now. So, when we lack constraints, that is in the maximum depth, if you don't set like a maximum depth, allowing the tree to grow until the very leaf is like pure, the tree becomes highly sensitive to every data point you subject it to. And under these conditions, an outlier or like a slight noise in the data can force the tree to like create an entirely different splits to accommodate the specific points, leading to a totally different model. And if we also check on the aspect of Gini and entropy, so if we are trying to like compare between Gini and entropy, so the splitting criteria, if the choice of criteria may it be entropy or Gini impurity, uh, okay, they determine the mathematical engine of the split. So while both like seek to like maximize information gain or maybe purity, they may choose a different feature to like split on. And at the root or at the decision nodes, if the data changes slightly, it contributes to like structural instability. And the third reason is it comes to train and test split. So because the tree is non-parametric and it learns from simple decision rules from the specific data they see, the way you partition your data using the train test split really matters. So if you're training like a set, if the training set changes slightly, for example, by changing the random state, say from if you had set the random state to say 42 and you change it to something like 67, the root node might choose a different feature to start with, which fundamentally changes the entire tree. Yeah, so to manage instability, we can check on the maximum depth, the mean sample split, and also the ensemble methods. Yeah, so that is the right way to go through that question.
Nice. I think I've learned something from that one. You've described it really well. So yeah, something new for me.
Mm. So would you love to take us through the pros and cons, the overfitting of decision trees?
Yep. Okay. Yeah, so I believe I think the advantages are um, for trees is highly interpretable and easy to visualize. So um, basically, using the trees itself, it's easy. The visualization is actually something that uh, what is being presented is for anyone who is interacting with it is able to understand and comprehend what is being displayed and what is being inferred from that one. Another one is it requires minimal data processing. So I think no scaling is needed for this one because data pre-processing is very minimal for this one. So yeah, then it handles both numerical and categorical data. Um, I believe those ones are the ones that I have. Then disadvantages of overfitting. Disadvantages of I believe this is classification and am I looking at the right thing? But overfitting a vulnerability to noise in data. So that's one of a disadvantage. Then instability, high variance, small data changes change the tree. So because of that, that causes instability on the tree or the data. The data itself with minimal changes can cause the tree to have, as Beth has said, that when you have data that is what's it called? Um, you've mentioned that when you have outliers that could cause the performance of the tree itself. So that's another thing. Um, yeah, something on combating overfitting. So you can combat overfitting by limiting the growth of the tree using maximum depth so that it reduces overfitting itself. So we have minimum sample split. So minimum samples required to split a node that will actually um, curb or combat overfitting itself to make sure that if you have a minimum sample split, then um, this will be easier for you to actually split a node and work with that node in a better way. Yeah, I think that's what I have.
That's great, husband. So if we try to like go deeper into decision trees, um, uh, I don't know if we have enough time to like do a hands-on. So maybe I can. Okay, maybe I can take you through on the relationship between like depth and accuracy. So So when you're trying to like find a balance for accuracy in a decision tree, it requires managing the relationship between the model's complexity and its ability to generalize new data. So as the tree's depth increases, the model's accuracy on like the training data and the testing data will typically behave differently. So to to show more on the relationship between depth and accuracy is we have three definitions we really need to put in the fingertips. One is underfitting. So when we talk of underfitting, we mean low depth. So if a tree is too shallow, such as a depth of like 1 or 2, the model is too simple to capture the underlying patterns in the data, and this results to like a low accuracy for both training and the testing data sets. And then we have the optimal depth. I don't know if I'll trace the graphing I had done. So the optimal depth, if you add depth, the model learns more complex routes. So what do I mean? Um, when so when you're talking of optimal depth, this is like the sweet spot, the sweet spot that often is around the depth of like 3 to 4, and this is where the accuracy is mostly at its highest. And when we talk of overfitting, so this is where we have like the highest depth. So when the tree becomes too deep, it starts memorizing noises and outliers. And these outliers mostly come from the training data set rather than from the actual trends. So while training accuracy may reach like 100%, testing accuracy will often stagnate or drop because the model cannot generalize the unseen data. Let me try and trace that. Let me try and trace it, then I'll share it with you. I don't know if I'll be able to trace it. Let me see. Yeah, I've been able to. So give me 1 second. I share it. Um, nice. So this is what I mean. So let me share my screen. Uh, so share. So I was trying to train my uh model on decision trees using the load iris, and the load iris is a data set. It's mostly a toy data set that is inbuilt in scikit-learn data sets. And as you can see, I found the accuracy as 1. But if you see, when I use the um let me share this screen, share this tab instead. I hope you can see this graph. This is exactly what I was trying to explain. So what I was saying is, you see, from 1, let's assume this is our 1 to about 3. So our 3 is here. So here we have some sort of underfitting. And what do I mean by underfitting? Our tree is too shallow, and our model is too simple to capture the underlying patterns in our data. And this results obviously to low accuracy for both training and testing. And as you can see, when we look at our data from around 4 to around 6, this is where we have the perfect fitting. And this is what we call the optimal depth. So if you look at this is our optimal depth. And what generally our optimal depth does, it adds, it's like I said, it's the sweet spot. So this is where our data set is learning more accuracy, and the accuracy is actually at its best. And then we have the aspect of and overfitting. So this is where we said that the data set gains so much noise from the outside data sets, and mostly the noise comes mostly from the training data set rather than from the actual data set. And this is where we find that the data either drops, the graph either drops the accuracy will either drop, or it will stagnate like ours did. So I think I used split. I think there is one I used split. I used the let me check if I can. trace it. Yeah, I use the grid search method. Yeah, let me share. I hope you can see this. So this is the graph. This is the pattern I was actually looking for when I used the grid search method to so I imported the needed libraries. So mostly we use scikit-learn for machine learning. So I use the same data set, the iris, the load iris. The load iris data set is used to look at plantlets, the small seedlings in plants, and generally see how how tall they can get in a period of in a time length. So I loaded and split by data. So as you can see, I read the data, I did the test train split, and my target was, as obviously we use 20% for training and the other 80% for training. So I used 20% for my training and I put the random stage to 42. And then I try to define the parameter grid. So this is where I was checking the depth to test. So I set my maximum depth to on a range of 1 to 10, but the best fit is usually 4. So, and then I initialize the grid search with the cross validation, and this is where I use the grid search CV, decision tree classifier, and I also tried to check on the output results. And I was able to evaluate the final test set. And as you can see, like I said, the best maximum depth is 4. And if you can compare, the best cross validation accuracy is actually 94%, and the final test accuracy is 1%. So that is generally what I tried playing along with data, and it's quite interesting. So that is basically in a nutshell what uh, so in a nutshell that is basically what decision trees are. So I don't think there's anything much to add. Osborne, do you have anything else to add?
Not exactly. I think you've wrapped it up really well. Yeah.
Okay, so maybe we can stop it at that, and next session we shall go in more deeper. So we shall move from a decision tree. So I love to think of it like a like a pattern. So we've started with a decision tree. So next time what we shall do random forest regression. So you've grown from a tree to a forest. So let's brace ourselves for our next session where we shall be handling random forest regression.